So before I come into QCon, I had an interview with the chairman of QCon, and he mentioned that the talk after lunch is really usually a tough one because people tend to get sleepy. So they usually try to arrange some energetic talk for the one after lunch. I'm not sure if there was some thoughtful arrangement for me, but look, I'm here to keep you guys awake. And to make things a little more complicated, I'm still jet lagged, so it's the worst time for me in California. So I have to keep myself awake. So let's see at the end of the talk, I can accomplish both goals. Anyway, I'm really excited to have the opportunity to come to London to talk about how Netflix uses Kafka. Netflix started to use Kafka in 2013, and we are probably the largest Kafka operator in AWS cloud. And today, our global footprint will be over thousands of brokers. Okay. So brief introduction about myself. I joined Netflix in 2011 with the cloud platform team and have had the opportunity to work with Sid and Danny, who is the speaker in the morning. In the cloud platform team, I worked on a couple of infrastructure projects, including dynamic properties and the Netflix internal web services framework, both of which are open source as RKS Ribbon in Netflix OSS. And about 3 years ago, I joined the real-time data infrastructure team at Netflix, where I started to work on our Kafka strategy. I was the Apache Kafka contributor for Keep36, Rec-Where Partition Assignment. So this was added in the Kafka 0.10 release. It was the second most important feature coming after Kafka streams in the 0.10 release. And it was a significant improvement for fault tolerance. So I would like to start my presentation by showing you the general microservices architecture in Netflix. So Netflix is the pioneer for operating microservices in cloud environment. And today we thrive on hundreds of microservices. So this picture shows the microservices architecture in tiers. So on the left side, we have our proxy tier, where we get all the user requests, and we do a little bit of transformation or processing, and then we forward those requests to the central API services, which is the bright dot on the left. And from the API service, these requests will be fanned out to hundreds of middle-tier microservices. So you may be wondering, where is Kafka in this picture? Well, it turns out that Kafka is everywhere. Just imagine that all those hundreds of microservices are either producers or consumers to our Kafka service. And on top of that, we have our hundreds of streaming processing jobs running in containers. And they are our they present the major fleet for our consumers. So operating Kafka in a cloud environment with hundreds of microservices accessing us represent some unique challenges. So today I'm going to go through some of the interesting challenge areas. And also, if you have attended my friend's Danny's talk in the morning, I feel like some of the areas, like size does matter for a stateful service, and multi-tenancy is becoming more and more important. These are becoming the common themes for distributed stateful services. So even if you don't know Kafka, I hope you can get something out of my talk. So the first thing I'm going to talk about is availability. So operating in the cloud means network failures or hardware failures are well expected. So how do we minimize the impact to our Kafka service and make sure we can keep a very high message delivery SLA? And the second, scalability. With With Netflix viewing activities fluctuating all the day, and the services around us doing auto scale all the time, how do we scale Kafka to deal with traffic changes? And finally, multi-tenancy. As our Kafka topics become more and more popular, a lot of clients come to our service, and they are all trying to compete with limited resources. So how do we make sure that everybody have a fair share of the resource? So for those of you who don't know Kafka, or you are not familiar with Kafka, I would like to give a very high-level overview. So Kafka is a distributed streaming platform, and at its core are replicated and partitioned logs organized in topics and partitions. So in the Kafka ecosystem, we have three components: producers, consumers, and brokers. A producer produces a series of records to one or more topics, and each record will be appended to the end of a partition as illustrated on this diagram. And for consumers, they can subscribe to one or more topics, and they can also fetch records from corresponding partitions. And Kafka uses the offset of a record, and they use that to keep track of the consumer's positions. So there are two major use cases of Kafka in Netflix. The first one, as Sid mentioned, is the data pipeline, where we reliably transport data from one application to another or from one system to another. And the other use case is streaming processing, where we write real-time streaming applications to transform or react to the streams of data. And there are two major categories of data that flow in our system. The first one is business and analytical data. So this includes all the events that we use to track how users interact with Netflix services. And they also include device logs. So these logs will be batched on our playback devices and then sent to our proxy, edge proxy service, and then forward to Kafka. And they can also include A/B test results. So Netflix is a data-driven company, so at any time we have tons of A/B tests going on to determine what would be the best decision for our business. And the second major category is the system-related. So these are typically application error logs, as well as some distributed tracing information. And we use those information to gain insights into our system, and also for some debugging purposes. For both categories of events, they have huge volume, but they are non-transactional. And for most of our topics, event ordering is not important and therefore not required. And just to give you some ideas of the Kafka scales running in Netflix, we're currently operating more than 4,000 brokers in about 50 clusters in 3 AWS regions, 2 regions in US and 1 region in the EU West 1, which serve I think most of you. And we have more than 1 trillion, we process more than 1 trillion messages per day in our Kafka system. And on New Year's Day of 2018, we reached a new milestone of processing more than 2 trillion messages. So on that day, we processed 2.2 trillion messages, including 1.3 unique messages, which is equivalent to 8 petabytes of data. So this is a typical Kafka cluster look like in Netflix. We have about 20 to 200 brokers in a cluster. Each broker instance will have 4 to 8 cores, gigabit network, and 2 to 12 terabytes of local disk. Our brokers currently operate on Kafka version 0.10.2, and we usually, we provision our Kafka cluster within one region, but we make sure that each Kafka cluster will span across 3 availability zones in AWS. And we use rack-aware partition assignment to create topic. So basically, the rack-aware partition assignment will ensure that different replicas of the same partition will be distributed to different racks or AWS zones. This is a way to achieve high fault tolerance, even if like the whole availability zone goes down. And occasionally, we use Mirror Maker to do cross-region data replication. But we only do that for a handful of our topics. So in the next few slides, I'm going to go through some of the challenges and the strategies that, that have been involved to deal with challenges. First one is availability. So everybody wants their Kafka cluster to up 24/7, 365. But exactly how do you define Kafka's availability? So we would like to think of Kafka's availability as the ratio of messages successfully produced to Kafka versus total attempts. So let's say you have, you produce 100 messages, you try to produce 100 messages, but one does not get into Kafka, then your availability is 99% in this case. So here I'm showing you a metric, which is the producer message drop rate, which happened at an early day of our Kafka operation. So you can see that this incident happened, lasted a few hours, and at certain times, our producer message drop rate reached almost 100%. In fact, we have tried different ways to recover from that failure, including rolling restart all of our brokers. But none of the approaches that we have tried helped us. So luckily, that was the first and the last major incident that we observed on Kafka. And we have come a long way to improve our availability to 5 nines and usually 6 nines recently. But that incident had a profound influence on how we operate Kafka. We realized that Kafka as a stateful service can go into a bad shape, and it will be like a one-way ticket. So the only way to guarantee a high SLA is to do failover and do that fast. So that's for availability. Our second challenge is scalability. So let's say we released a fabulous show. And by the way, I hope I did pick the right example for this location, for this audience. So we released a fabulous show, and here comes some good news and bad news. The good news is we attracted a lot of users to come online to start streaming the new show. And the bad news is that we will see traffic spike like this. And it usually means some problems for our Kafka cluster if our Kafka cluster is under-provisioned. So how do we deal with it? So on this slide, I'm going to show you how we deal that problem with our stateless service. So on the slide, the top of a metric, we called the stream start per second. So it is a core measure that we use to see usually how much the overall traffic is for Netflix. And the bottom metric is the instance count from a stateless service. So you can see that the stateless service can auto-scale pretty well according to the traffic pattern. And at the peak, the stateless service can reach its capacity peak. And when the traffic goes down, the stateless service can also scale down and stay at a pretty stable level. So that means a huge savings in terms of operational cost. So by contrast, this is the instance count of one of our Kafka cluster. And you can see this is a very boring flat line. Why? This is because Kafka is difficult to scale. And usually we have to over-provision our Kafka cluster statically according to a presumed peak traffic. So why is scaling difficult for Kafka? Let's first review our options available to scale up a Kafka cluster. So the first option available is that you add brokers, and then you add partitions to those new brokers. So it currently doesn't work well with keyed messages because when you add partitions, the order of the keyed message will be messed up. And there's also a practical limit of number of partitions you can have for a Kafka cluster. So according to the latest recommendation from Confluent on the 1.1 release, you can have roughly around 100,000 partitions for your Kafka cluster. That being said, there's a new proposal that's being worked on right now, KEEP 253, in order message delivery with partition expansion and deletion. So there's already some heated discussion going on in the Kafka group, Kafka dev group. And this is actually referred to by some of the users as the holy grail of Kafka scalability. And so definitely keep an eye on that. And the second approach to scale up is to add broker and do partition reassignment. So the biggest problem with that is there's a data copying process involved, because when you bring up new broker and you reassign the ownership of the partition, the new broker has to copy the data of that partition from the current leader before it can function as a leader. So this is a time-consuming process, can usually takes about a few hours, depending on your retention period of data. And during that period, there will be a significant increase of network traffic, and that kind of replication traffic will compete with your production traffic for the limited bandwidth of your Kafka cluster. Just imagine that it's 2 a.m. in the morning, and you see a spike of traffic, and you need to scale up Kafka cluster. Are you comfortable of doing partition reassignment at that time? Probably not, because by the time you are done with your partition reassignment, everything is probably over. So given all those challenges and limitations from a single Kafka cluster, we start to think, instead of looking inside a Kafka cluster for scalability and availability solutions, can we scale out and try to utilize multiple clusters? So once you start to migrate from data center to cloud, one benefit you will immediately notice is the speed and easiness to bring up a new cluster, even if it's a fairly big size. While it may take months to provision a new cluster of hundreds of instances in a traditional data center with some kind of manual approval process, in cloud, it just takes a few mouse clicks and maybe just an API call to your service provider. So why not take advantage of that? So let's see how we can scale with multiple clusters to deal with traffic changes. And to start with, let's assume you have one cluster and you have a producer and a consumer. And now you see some traffic spike and you want to scale up. So what you can do is you can start to leverage a second cluster and create the topics on your second cluster. And the next step, you ask your producer to start producing to both clusters and consumer to start consuming from both clusters. So now you have your traffic go through both clusters. So you actually successfully finished a scaling up activity. And now the traffic goes down, and you need to scale back. So in order to achieve scale back, the first step you want to do is ask the producer to stop producing to the second cluster. But at that time, the consumer still have to consume from both, because it has to make sure that all the data have been consumed from the second cluster, or the data retention period has passed on the second cluster. And then you can stop fetching from your second cluster. You can then safely delete your second cluster and finish this scale up and scale down cycle. So here I'm going to show you how you can do topic move from one cluster to another as a way to achieve failover. So again, you have the one cluster to start with. And now you want to move the traffic from cluster 1 to cluster 2. So as a first step, you ask the producer to stop producing for the first cluster, but start producing to the second cluster. And the consumer, it still needs to, for the consumer, it will needs to consuming from both clusters until the data retention period has passed on your first cluster, or it has consumed all the data from the first cluster. Then the consumer can stop fetching from the first cluster. So with that, you have the traffic goes through the second cluster, and you have achieved your failover. So since I have to talk about failover, I would like to do a little bit deep dive to see how Netflix does Kafka failover. I want to first make a note that Netflix operates in the island model. That means we deploy all our applications in all regions. And each region can pretty much operate on its own, and there's very little cross-region traffic. So the goal of our Kafka failover is to ensure that we can recover from a Kafka cluster level failure that happened within a region. And we want to achieve that by doing switching client traffic to a different cluster. So the benefit of doing that is there's no extra cost or redundancy. There's no extra cost for redundancy or cross DC traffic. But in this case, because at a certain point, the same data for the same topic may land up in two different clusters, we cannot guarantee any ordering. And in best case, we can achieve exactly once for our consumers during that failover process, because there's no duplicate data in any of the clusters. But in worst case, if the original cluster is in such a bad shape that it can no longer serve fetch request, and then in that case, there might be some data loss during failover. So I would like to pause here a little bit and to sum up how multi-cluster can help us to achieve better scalability. First and most importantly, there's no data copying in that scale process. That means we can scale up fast, typically just within minutes. And with the multiple clusters, you can easily do failover by switching client traffic. And we currently implemented that extra capability to switch client traffic by some kind of dynamic properties integration in our client applications. So that means our client applications can react to runtime property changes without restarting their applications. But this approach does not work with keyed messages. As you can see in the previous slides, the ordering of messages can be messed up in this case. So this is still something we are trying to figure out, and we are trying to find a solution for that. And second, I want to show how you can improve Kafka's availability by having multiple clusters. So in this chart, you can see we will start with one cluster, and this cluster has a size of 12 brokers, and we assume we have replication factor 2 for that cluster. At some point, unfortunately, you will lose 2 brokers, because that 2 brokers represents all the replicas of a partition. You will likely run into some kind of data loss. But if we can divide up that cluster into 3 smaller clusters, but still have replication factor 2 on those 3 clusters, chances are that those 2 bad brokers will be located in 2 different clusters. And because for each of these clusters, it has replication factor 2, so losing 1 broker actually doesn't matter. So there's no data loss once we divide up the cluster. So that's just a high-level intuition on how multi-cluster can help with the availability. But we can actually approve it. So let's divide one big cluster into S small clusters. And let's assume that losing K brokers, let's assume replication factor is K in both cases, and losing K brokers will lead to some kind of data unavailability. We can prove that the set of smaller clusters can be S to the power of K minus 1 times more reliable than the one big cluster. So if you look at this formula, S to the power of K minus 1, it's actually fascinating. So that means you will get a lot of benefit by breaking up a cluster if you have large number of replication. And let's take some examples. If K is 1, that means you have replication factor 1. Then this whole thing is 1. That means there's no benefit of breaking your cluster. But if K is 3, means replication factor 3, which is a very common setup for a lot of use cases. And if you can break your cluster into 10 smaller clusters, then that's 10 to the power of 2, and suddenly your clusters become 100 times more reliable than the original 1 cluster. And if you don't believe me, here's the math. We basically want to compare the number of combinations to choose K brokers from a cluster of size n versus choosing K brokers from any one of the S clusters of size m. And if you follow the math, you'll get to the conclusion of S to the power of K minus 1. So aside from availability and scalability, we find that multiple clusters can also help us to deal with the challenge of high consumer data fan-out. So I'm going to use this picture to show exactly what I mean by high consumer data fan-out. So this screenshot is taken from our self-service portal. And each dotted path from the root, which is on the left, to the leaf, which is on the right, represents a consumer. So if you count, we have about 14 consumers for this very popular topic. So the data volume for that topic is 4 gigabytes per second. And with 14 consumers and the data being compressed on the broker, we are still looking at 20 gigabytes out required to satisfy all those 14 consumers. And that is already very challenging for even a big cluster. So how do we deal with that? So now let's look at this picture. We have 4 consumers for a Kafka cluster, and that cluster has just enough bandwidth for those 4 consumers. Now here comes the fifth consumer. And it also wants to consume from the cluster. Well, because we only have enough outbound bandwidth for 4 consumers, so this is not something we can do with the fifth consumer. It will exceed the outbound bandwidth for the cluster. So what are our options? A naive solution is just to add more brokers to your cluster to satisfy the bytes out. But with that approach, you are facing with a cluster with ever-increasing cluster size. And as I mentioned before, we don't typically like a huge Kafka cluster because they tend to lead to worse availability. So what can we do? So the solutions that we come up with is to create a second cluster and chain the second cluster with the first cluster. And then we have some kind of routing service. Basically, it's like a mirror maker that copying data from one cluster to another. So basically, the data will be copied from the first cluster to the second cluster. And then we assign 3 consumers to the first cluster and 2 consumers to the second cluster. So in this setup, we only have 4 consumers for the first cluster. So it will have enough bandwidth. And if more consumers come, we can simply add that to the second cluster. So with this kind of tree topology and with multiple clusters, you will find that actually it can scale infinitely to satisfy any number of consumers. So to sum up, what are the ideas behind the multiple cluster? So first, you want to break up your big cluster into smaller ones. And those smaller clusters are usually mostly immutable clusters. So what I mean by immutable, it means we don't do partition reassignment to our Kafka clusters. And the only operation that we do is creating clusters, destroying clusters, creating topics, delete topics. And then once you have your multiple clusters, you can scale up and down by adding or removing clusters. And as I proved in my previous slides, small clusters tend to have better availability than a big cluster. But you can even improve that availability by doing failover with client traffic migration. And secondly, to satisfy the consumer bytes out, you can connect clusters with a routing service in between. And as I mentioned before, the routing service is basically like mirror maker that copying data from one cluster to another, but they can also do some simple ETL work. So now you have multiple clusters, and you will find that you will see the overhead increase for managing multiple clusters as opposed to managing a single clusters. So that's where you need some kind of management service for automation and orchestration and to reduce the chance of human errors when operating on multiple clusters. So I would like to think about this multi-cluster architecture as a transition from pets to cattle. So for pets, they have their own identities, and they require personalized care. But for cattle, they have no identities, and they can be produced in mass scale. So it becomes a non-event if you get or lose a few cattle. So we would like our Kafka clusters to behave like a cattle, where they can be easily created or destroyed for certain purposes. So with that, I'm showing you this complete picture of our multi-cluster Kafka service at Netflix. So on the left side, we have our event producers, and they produce events to a set of Kafka clusters, which we call fronting Kafka clusters. And those event producers are basically every microservices in Netflix. And they produce events in 2 ways. One is through an HTTP proxy, or they can use a Java client library. In either way, they have the capability to interact with multiple clusters. And once data get into our front-end Kafka cluster, they are consumed by our routing service, which is currently implemented on top of Flink. And our routing service further sends those events to downstream sinks, including S3, Elasticsearch, and a different set of Kafka cluster, which we call consumer Kafka clusters, where they will be consumed by any regular consumers or streaming and processing jobs. So note that we have this unique kind of two hierarchies of Kafka clusters. So this setup is used to achieve two goals. One, as I pointed out, it can help us to deal with the high consumer fan-out scenario. And a second purpose is that with this setup, we can achieve a very good isolation between the producer and consumers so that we can do easy multi-tenancy management. And I will talk about multi-tenancy management in later slides. Sorry. Okay, so in the middle of this box, we have our management service. And as I mentioned before, it's used to carry out automations and orchestrations. And in the management service, we also have a user interface, which we call a self-service, where a user can come to our system and request for streams or topics, and they can also specify what kind of operations they want on the stream and what kind of things they want to send those events to. And our management service also have a admin portal. So this is for our own purposes, where we can go in and manage all of our Kafka cluster from a single place. And we can also easily carry out automated operations like failover from this admin portal. So that's for availability and scalability. So now I'm going to talk about multi-tenancy. So just to give you an idea of the problems we are facing right now, looking at our looking at the cluster with the largest number of clients. So for that cluster, we have over 400 applications or microservices accessing the cluster. And at the peak time, we have over 33,000 of network connections per broker. So with that kind of scale and hundreds of microservices being all our clients, you can easily get into a situation like this. So this is what I call a problem kid. Whatever you have, he likes to take it all. And this is what happens to our Kafka cluster. So we start with our Kafka service open to everyone in Netflix. And it actually fits quite well with the Netflix culture, which says freedom and responsibility. But as the service becomes more popular, we started to observe problems that one client can saturate the inbound or outbound bandwidth of a broker, and it creates all sorts of problems for us. So it will slow down the other consumers. It can even store some consumers and cause some streaming processing job failures. And it will slow down the replication, which is likely to cause a stability problem for the whole cluster. So we determined that we want to do a proper multi-tenancy management. And the goal of our multi-tenancy management is to first get to know our clients, establish their true identity, and then make sure that they all have a fair share of resources and they will not affect each other. And finally, we want to do a better capacity planning with all the details we have on our clients. So I would like to think that the multi-tenancy management is no more complicated than hotel management. Just think of the process you have to go through to get into a hotel room. First, you have to make a reservation. So it is equivalent to the client registration process in our multi-tenancy management, where our client will come to us and tell us the topics they are interested to consume or produce. And the second step to get into the hotel room is to check in with front desk and show your ID. This is the authentication in multi-tenancy management. And the final step, before you can get into your hotel room, is to obtain a key. So the key is used to guarantee that you will get what you reserve for, but nothing more. So this is the authorization, and is also equivalent to Kafka's ACL and quota. So of all these three steps, I find that the most challenging but most critical step is authentication. So in the old days, when we need to identify our certain clients for our Kafka cluster, we usually have some usual suspects that we can ask for, that we can email or ask them in the Slack channel, or sometimes we can do code search to find all the references of certain topics within the source code of Netflix. And sometimes we can do TCP dump to find who is trying to access us. But we soon realized that none of this approach scale. So what we decided to do is to do proper authentication and authorization based on our Netflix security system. So the first step that we have done is to require every client to communicate with us via SSL. And we require the client auth for all our clients. That turns out to be a not difficult task because our security system has already paved the path for us by installing a standard client cert on every Netflix instance. And that client cert includes all the information we need, like the host name, IP address, and most importantly, the application name. And the second step that we have done is to integrate Kafka's authorization with Netflix authorization service. So Netflix authorization service currently only works for RESTful services. So they only understand HTTP method as some kind of operation and URL as some kind of resource. So to speed up the integration with our authorization service, we decided to do a mapping from Kafka operation to HTTP methods, which I'll show a detail on the next slide. So after going through all these efforts, we find that we are able to impose ACL and quota on true client, true application identity. So in this slide, I'm going to show you the process of authentication and authorization for our Kafka service. So you have an application X here who wants to produce some records. And we have our authorization service, which is basically a rules engine that operates on a preset of predefined rules. So the first step for that application to produce some record is to first establish a SSL session with its client cert. And our Kafka broker will extract the application name from that client cert. And then the application can start to create some requests for write to a topic foo. So once we get those produce requests or write requests, our broker will in turn ask a question from our auth service. Basically, it will ask the question whether application X has the permission to write to topic foo. And here, we map the write topic operation to the HTTP method put, followed by a path /topic/full because that's the only thing that our auth service understands. So let's say the auth service returns a yes on this answer, on this question. And our broker can then accept that produce request and write the data into the log and then send the successful ACK back to the producer. And that completes the authentication and authorization for our Kafka operation. So that's the end of my talk. It has been a long talk, and I hope everyone can enjoy some bit of that. And it's perfect okay that you are not 100% clear on certain aspects of that. But I want you to walk away with some high-level ideas and maybe start to make use of those ideas. And specifically, if you hit a bottleneck of scalability and availability from a single cluster, try to scale with multiple clusters. That will give you a lot of benefits, like being able to scale up and down with traffic by just simply adding and removing clusters, doing failover by migrating client traffic. And then you can also have the ability to chain clusters to deal with the high consumer fan-out problem. And for multi-tenancy, the most important step is to do proper authentication and authorization. And that will lay you a very good foundation for your multi-tenancy management. And you can achieve that goal by integrate with your SSL infrastructure and possibly your own auth service. And that was it. Thank you very much.